This is Unit 1, Video 5. In this unit, we are talking about the structure of the atom. And in Part B of the unit, we'll talk about electrons, because the biggest part of the atom that concerns us will be the electron cloud. That's where all the chemistry occurs. So we'll start talking about electrons, their structure, and their behavior. Now, in order to understand electrons, we have to understand light. And actually, the way scientists first came to understand how an electron works is by studying light. The reason they did that is because light is released by electrons. So we can actually have a glimpse inside the atom by analyzing the light that comes from the atom. So we have to study this question: what is light? Light, scientists came to understand, has what's called a dual nature. So it behaves as both a wave, and wave indicates energy, like think of an ocean wave, and a particle. Now, particle indicates matter, and electrons are matter, and a wave, energy, is not matter. So electrons kind of are related to light, which has this weird dual nature as matter and not matter. Light is not considered matter, it is considered energy, but it has this nature of particles. So we're going to look at both of these features of light. So to understand light as a wave, we would go back to a very early experiment, actually done by Newton, Sir Isaac Newton, and he shone light. If you shine light through a prism, the prism will actually split light up into its different rainbow colors, and everybody knows the Roy-G Biv, and this is called refraction. Light is refracted, bent into its colors, and so that's how we say that white light is actually composed of all the colors of the rainbow. Now, this allows us to see deeper into the structure of light, and this is due to the fact that, so here's an actual picture of the same thing happening. You can do this with a prism at home. You can even do it with just a mirror and some water. And a similar thing happens with, these used to be pretty popular, with a compact disc. This idea, or this concept, is called diffraction, which is related to refraction. But refraction has to go through a substance. This would be refraction here. Diffraction kind of bounces off the surface, but a similar effect takes place. The really, really tiny tracks on a CD that have to be read by a laser do the same thing. They actually break light up into its colors, and then that bounces back at us. So you can see this effect clearly, pretty easily. Everyone is aware of it. And this is because light behaves as a wave. Now, a wave has two features that we want to study. It has what's called the wavelength. Now, we're going to symbolize this with this letter. This is a Greek letter. This is the Greek letter L. This is called lambda. And it measures the distance between two waves. So here is our wavelength. What you would do is measure from the top of one wave to the top of another. The top of a wave is called the crest. The bottom of a wave is called the trough. You can also measure from the trough to the trough. You'll actually get the same distance. Either way, this will be the same. But usually we say from crest to crest. And this will be measured in meters. So that would be the first feature of a wave we want to consider. The second feature of a wave will be its frequency. And the frequency is the number of waves that pass the same point in a second. So usually we express this as waves per second, or 1 over a second. Sometimes this is actually written as seconds to the negative first, because anything to the negative first power actually means 1 over that. Or expressed as hertz, after a scientist that first came up with this concept, H.C. So you can see here in the top wave, if we count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can say this wave has 12 hertz. Whereas the bottom wave, 1, 2, 3, 4, 5, simply has 5 hertz. So the bottom wave has a lower frequency, the top wave has a higher frequency. Now you'll also see that the wavelengths are different, and we'll see this relationship will be really important. In this case, you see that in a higher wave or higher frequency wave, the wavelength is shorter. In a lower frequency wave, the wavelength is longer. So this is what we call an inverse relationship. As frequency increases, wavelength decreases. They are inversely related. So a higher frequency wave has a shorter wavelength. Lower frequency wave has a longer wavelength. Now here is the electromagnetic spectrum, and it's named electromagnetic because it has electric properties as well as magnetic properties. So you can kind of see how the idea of the electron maybe influences light, even though that refers to something a little more complex. So all the light that we can possibly see or detect is displayed here in the electromagnetic spectrum. It goes from a really low frequency, which refers to radio waves, to a really high frequency, which refers to gamma rays. Now, gamma rays are really dangerous, and you don't want to be in contact with those. They'll damage you really quickly. But a very tiny portion of this is the visible spectrum. This is the portion of it that we can see. This is the portion that breaks down Roy G. Biv from red over here all the way to blue on this end. Now, if you take a look, the graph here shows frequency on the bottom and it shows wavelength on the top. So for visible light, we are going from about 750 nanometers down to 400 nanometers. Notice the wavelength is decreasing because the frequency in this direction is increasing. And 750 nanometers is, if you convert it to regular meters, will actually be 7.5 times 10 to the negative 7th meters. And this is actually, another way of thinking about it is this is 0.75 micrometers. So it's actually a little smaller than a micrometer. And that comes in right here. This would be 10 to the negative 6th. And so visible light spans about half of an order of magnitude. So just a little bit smaller than 10 to the negative 6th. 10 to the negative 6th is a micrometer, a micron. So this is why visible light is smaller than a micrometer, and that's why we can't really see anything smaller with a visual microscope, much smaller than a micrometer. We have to go into a special type of microscope for that. So, and this would be 0.4 of a micrometer, essentially. Or another way of saying it is 4.0, we'll say, times 10 to the negative 7th meters. So this is the visible spectrum of light. This is what we can see. Now, there are animals that can actually see into the UV region. This is ultraviolet. If you keep increasing the frequency, you'll get into ultraviolet. Usually birds and bees can actually see into this region. Now, we're not going to talk about the birds and the bees in this lesson. Don't worry. We'll do that in class. On this side of it actually is the infrared region. There are some reptiles. There are some animals that can actually see into the infrared. But we're restricted. We have a pretty small sliver of this whole portion that we can see. But we can definitely detect way into the infrared. We have instruments that can actually detect all of this. Infrared, notice, spans about 2.5 orders of magnitude, whereas visible light is only about half an order of magnitude, so quite a bit more. Microwaves, we can definitely detect them. We have technology that is made based on these waves, the microwave oven, and this is also about 2.5 orders of magnitude. Radio waves are pretty big. Cell phones and radios, a lot of things use radio frequencies to communicate, so we're definitely using instruments that can detect this portion of it, even though it's all invisible. We can also detect ultraviolet rays that spans about 1.5 orders of magnitude, and X-rays about 3 orders of magnitude. And then beyond X-rays or gamma rays, which are really, really high energy rays, usually associated with anything outside the Earth, naturally at least. X-rays, some X-rays make it into the Earth, but they get more and more energetic here. So we're going to focus a lot on this portion right here to see how electrons behave, and understanding light is really important for us to understand how electrons are behaving. Okay, so quick little question to see if you understand how to read the electromagnetic spectrum. Here it says, using the spectrum, electromagnetic spectrum, list these colors in order of decreasing frequency. Now, these numbers here are wavelengths. This is 400 and this is 700. So if wavelength is increasing this way and frequency is inversely related, that means frequency is decreasing the same way. So we can say this is decreasing frequency. because it's increasing wavelength, as we see. Which means we just have to go from blue to red. So it looks like blue will have the highest frequency, and then it goes green, and then yellow, and then red. And that's the idea. So pretty simple, just for us to see and understand the difference and the relationship between frequency and wavelength. Pause the video and do the same thing with these and see if you can do it without having to refer to the electromagnetic spectrum, so you can roughly understand the positions of these. The biggest thing is infrared will be right next to red, ultraviolet will be right next to violet, and that's really the way to do it. Try to do it without looking at the spectrum. Now, light can also be considered to be a particle. We just talked about light as a wave. Now let's see light as a particle. And this particle is called a photon, and they try to, use the same idea as a proton or an electron or a neutron. So this proton business refers to light as a particle. Now it has energy. This particle has energy, but no rest mass, which means if you were to slow light down, you could not weigh it, because technically light is not matter, light is energy. But it's really strange that it has, it says no rest mass, which means when it's moving, you can think of it as having mass when it's moving. That's because it has energy, and energy, things with energy, can affect matter. That's the idea. Now, a particle of visible light has, so visible light would be, anything from roughly red to roughly blue light, has about 4 times 10 to the negative 19th joules of energy. That's a really, really tiny number, and that's because we're talking about just one little photon of light, one little particle of light. Now, it all depends, as you'll see, on the frequency. So light with a higher frequency will have higher energy. Light with lower frequency will be even lower than this. Now, a joule is the unit that we'll use for energy. Hopefully you've seen this before. If you haven't, we will discuss joules a lot. And joules are related to another energy unit that we want to introduce here called the electron volt. And this is, 1 joule is 6.242 times 10 to the 18th electron volts. You don't have to memorize this number, but electron volts are essentially the energy you can think of a single electron. That's why you need a lot of them in order to build a joule, because it's really like the energy on the order of an electron. And a tiny packet of energy is called a quantum of energy. We will refer to this word quantum. Quantum means a specific amount, or a discrete amount. A tiny specific amount of energy is a quantum. So a particle of light can be thought of as a quantum of light. Usually it's referred to energy in this case. So if you take a look at the electromagnetic spectrum, then we can see how energy is related to frequency. So as wavelength increases this way, we know frequency must decrease, so frequency increases this way. And along with frequency, notice, goes energy. So a higher frequency wave has more energy. So radio waves have the least energy, which is a good thing because we're bombarded with radio waves at all times, through the radio towers, and that's how our cell phones communicate. So we don't want that to have a lot of energy to damage us. But something like X-rays have a lot of energy, really, really high frequency and a lot of energy. And gamma rays all the way out here have even more energy. So the visible spectrum is almost in the middle, a little to the left of middle, and that's the relationship between energy and frequency. All right, we'll take a look at this concept in video 6.